All right, this officially begins our third session featuring Kevin Teakell, PE, Senior Manager of Government and Industry Affairs at AAON, and he's going to be covering A2L refrigerants. If you're joining us live, remember to grab your PDH certificate below after this presentation. There's one specific to New York, and then there's one for the other states that we're approved in, and you can see that list below. If you're listening to this or watching it in the future on our YouTube channel or podcast, just check the show notes in the video description and you'll see my email. You could email me and I'll gladly send you the PDH certificate. Kevin's expertise in regulatory standards and refrigerant technologies makes him a leader in the space, and his insights today are valuable, and we're so super glad you're here. Please ask questions in the chat. Kevin is really one of the industry leaders on this topic. If you have any questions, please drop them in the chat, and I will shut up and take it away, Mr. Teakell.
Well, good morning / afternoon, everybody. Just a little note as we get started here. If you see me waving my hand around like a crazy man, it's because my lights auto shut off at like 20 minutes. So I might have to do that a little bit. We'll see. No problem. Thank you, everybody, for today. Got a lot to talk about here. This is a big transition that's really been coming at us. I've been in the industry. I've been at AAON for 28 years. And this is probably the biggest transition I've seen. And it really impacts the entire industry. You know, we've had previous transitions that impacted maybe manufacturers more, but this one really kind of covers everybody. So glad you're here today so we can kind of talk through some of these changes and learn more about it. So let's go ahead and get started. So today we're going to talk a lot about new refrigerants. Okay, so we're going to talk about some of our safety standards as well. You know, historically, for the industry, we've been using a safety standard known as UL 1995, and that governed all the testing and all those kinds of things we had to do to make sure our products were safe. But now we have a new safety standard that covers all these appliances, you know, and air conditioners and appliance. It's called UL 60335-2-40. So it's got a lot of new requirements for us as far as a manufacturer for how we test our products to make sure they're safe for these new refrigerants. We're going to talk about some of the regulations as well as the safety that goes along with these new refrigerants. We'll talk about some of the refrigerant detection systems as we apply them. You know, there'll be some differences between manufacturers, but in general, there's some things that are very common. And then we'll kind of compare some of these refrigerants, and then we'll close out talking about some of the refrigerant alternatives that are out there to maybe even go to lower GWPs, which we'll talk about as we go through this. So the big thing here is governments around the world have decided we need to change our refrigerants to a lower GWP. Okay, GWP stands for global warming potential. So we're going to be changing all of our refrigerants to these lower GWP refrigerants. So the unfortunate thing is that any of the replacements that are out there for R410A, which is what we use in air conditioning today, are in a new category kind of known as mildly flammable. Okay. So that may sound a little scary, but let's kind of talk through this. So this chart here on the right is from ASHRAE 34, which talks about refrigerant safety. It's the safety classifications for refrigerants. And historically, there's kind of two digits that make up the safety classification for these refrigerants. So the first digit refers to toxicity. So it's either an A or B for technically lower toxicity, which a lot of people will kind of call non-toxic, and then B for higher toxicity. So you've got an A or B in that case. And then as we look at the second digit, we've got a 1, 2, or a 3. So a 1 is technically no flame propagation. Now, a lot of people kind of call this non-flammable. But as you'll see in the next screen, we can't actually get these to light. So it's technically no flame propagation. Then we have 2 for flammable and 3 for higher flammability, or very flammable, or almost in some cases even explosive in certain concentrations. So and then you also notice we've got this 2L, okay, so this class 2L, and that's what these new refrigerants kind of fall into. Okay, as these new refrigerants were developed, it was kind of realized, well, they're not as flammable as a 2, but they are more flammable than a 1. So they came up with this new category, that added this L in there for lower flammability. So it is a pretty low flammability risk. Okay, things like electrical components, right? You have a contactor or a relay or something. Those, when you engage those, they put off a little spark, but there's not enough energy in that spark to actually light one of these refrigerants. Now, there is enough energy in that spark to light something like propane, but not one of these refrigerants. By definition, it's a very slow-moving flame. So to fall in this 2L category, it has to move less than 4 inches per second. So that's pretty slow. Okay, that's certainly not a big explosive event like you would see with a much higher flammability refrigerant. And in fact, the refrigerants we're talking about usually move about 2 inches per second, so they're even lower than that definition. It typically requires like a constant ignition source. So, I talk a lot about these refrigerants in that, they're kind of, I like to say they're kind of hard to light, kind of hard to keep lit. If you put a flame to one of these, we had a bowl of it here and we kind of lighted it, it kind of light, kind of flicker and stuff, not be too exciting. If you pull the flame away, a lot of times that'll kind of go out. So, like I said, kind of hard to light, kind of hard to keep lit. We do have, in a lot of cases, new compressors. It depends on the compressor manufacturer. Some have gone with new compressors that are optimized for these refrigerants. Some have kind of made their compressors where they cover multiple refrigerants. So it just kind of depends. A lot of cases, like expansion valves are going to be new to perform with the new refrigerants. But the big change is now the addition of leak detectors in the systems to detect if we ever have a refrigerant leak. So that's all part of that UL 60335 safety standard, where we have to go through and install these leak detectors in our equipment. Now, the other unfortunate thing is, building codes never really recognized an A2L refrigerant. They weren't used before. So we had to go through a process to update building codes. And in some states, it's easier than others. Some states we had to actually go pass laws to make it legal to use these refrigerants. So we've kind of gone through a process to do that. Because building codes are on the model building codes anyway, are on a 3-year code cycle. So like, the International Building Code, it's on a 3-year code cycle. So we were unable to get these refrigerants into the 2021 code cycle. We've since got them in the 2024 code cycles, but states and cities and such don't usually update building codes real quickly. Okay, you've got, building codes it's kind of a slow process on purpose, because when things change in a building code, you've got tens of thousands of people that have to understand these changes and be ready for them and do all these things. So it takes a while to update building codes. But unfortunately, with the timing we were given from the EPA, we don't have the amount of time it takes to normally do this building code cycle on the normal process. So we had to, as an industry, really go through and work really hard to get this adopted in all these places. And I'll have a chart here in a minute that goes more into that. Most states are typically on a 2015 to 2018 building code. Okay, so it usually takes a while to update these building codes. And again, we didn't have the time to do that. So just for example, North Carolina, since that's where a lot of the inside folks are, is a 2018 building code. Okay, 2018 International Mechanical Code. So it just varies where you are. And in some states, you don't have a state building code. You have cities that have their own codes and different things. So it's kind of a patchwork across the U.S. as to the process we go through here. So this all kind of started through an international treaty, really. If you talk about refrigerants and how they've been changed over time, we can kind of start back in the early 90s with what was known as the Montreal Protocol, which was a UN treaty. And it's what got us off of ozone depleting substances, so ozone depleting refrigerants. So that's why we went from like R22 in 2010 to R410A, since 410A was a non-ozone depleting substance. So we had Montreal, and then governments around the world and such were starting to want to reduce the GWP of refrigerants. So during the Obama administration, the EPA tried to regulate refrigerants based on GWP, and they were sued over that and went to the Supreme Court. The Supreme Court ruled that the Clean Air Act didn't give them authority to do that. So industry kind of got together and decided, well, we really need some certainty, because certain places are going lower, and it really helps industry if we have certainty, so we don't have to deal with every state and every place that wants to make a regulation. So we got together and created what was known as the AIM Act, and Trump signed that into law in December of 2020. So the AIM Act followed what is known as the Kigali Amendment. The Kigali was amendment to the Montreal Protocol. And Kigali set forth a phase-down schedule for HFC refrigerants, or hydrofluorocarbons. Okay, so that's what we're going to talk about here. Now, since the AIM Act was passed, the U.S. Senate did ratify Kigali back in September of 22. So we've kind of followed all that. Now the AIM Act gives the US EPA the authority to do several things to reduce our HFCs. So there's kind of three parts to the AIM Act. The first part is what is known as an HFC phase down. Okay, so this phase down is where they're going to tell refrigerant manufacturers, the companies that actually manufacture the refrigerants themselves, to reduce the amount of supply that they can actually create and sell. So beginning in 2022 and 2023, there was a 10% reduction in the amount of refrigerant they could make from the baseline, which was kind of an average of 2013 to 2018 or something like that. So they could only make 90% of what they did in that baseline. And then beginning this year through 2028, it's a 40% reduction. So they can only make 60% of what they did historically. And then 70% less in 29, 80% in 2034, and then finally 85% less in 2036. So we're going to dramatically reduce the amount of these HFCs that are manufactured and put onto the market. So Europe kind of did this back in 2015, and when they did that, refrigerant prices increased about 1,000%. Okay, so the idea here is reduce the supply so the price goes way up, so we want to go use something else. Okay. Now it's important to note, so R32, we'll talk about some of these refrigerants a little bit, but R32 is one of these refrigerants we're talking about using to replace 410A. R32 is an HFC, so it's subject to these rules. It's also a component in the other refrigerants that would replace 410A, so which makes those an HFC as well. So you may be asking, why are we going to a refrigerant that's being banned here? And the concept behind this is we're gonna take everything else that uses HFCs, like commercial refrigeration and automobile air conditioning, different things like that. We're going to get them onto some other types of refrigerants, like an HFO, hydrofluoroethylene, or natural refrigerant, something else. Get them off of HFCs and leave the HFCs behind for air conditioning, because air conditioning really needs it. If we use some of these other type refrigerants, we really start to make some compromises that hurt it. So we're going to try to get everything else off of HFCs for air conditioning. And then the other part that we really want to try to do is encourage and increase the use of reclaimed refrigerants, which is where we recover old refrigerants out of an old machine that's being, end of life, or it's being serviced or something. Recover that refrigerant, take it to a reclaimer where they clean it up, bring it basically back to virgin refrigerant, and then we reuse that refrigerant. So we didn't have to make any new refrigerant. So that's kind of the concept behind all this. So we really need everyone's help to really encourage and improve the use of reclaimed refrigerants. So something we want to encourage our technicians to do. So then the second part of the AIM Act is what is known as the Technology Transition Rule. So this is where the EPA is going to determine for air conditioning, we have to have a GWP below a certain value by a certain date. So they go through all the various sectors and give them these rules. Now I'm only going to talk about air conditioning in this presentation, but so as we kind of go through this, there's a few definitions we want to set that the EPA put in this rule. So the first one's pretty obvious. A product is something that is manufactured in a plant. Okay, so it's manufactured in a plant, but it also means it has the refrigerant charged in the plant. Okay, so that's a very important distinction for a product. And then they define a system as something where you assemble it in the field. Okay, so you're basically going to take an outdoor unit and an indoor unit, you pipe them together, and you put that refrigerant in the field into the unit. So that's a system. So that's how they kind of define these two pieces. Now, the manufacture date for a system is the day that you put the refrigerant when you charge it in the field. Okay, so it's not actually manufactured technically to the EPA until you put the refrigerant in the field. So and then it's also considered to be a new system whenever you install a new condensing unit and a new indoor coil at the same time. Okay, so even though it may be you're replacing an existing system, if you replace these parts at the same time, it's now considered new and will be subject to the rules under this technology transition rule. Then they also have 5 specified components. So there's a condensing unit, a condenser, a compressor, evaporator unit, and an evaporator. So for these 5 specified components, there's no end date in the rule. Okay, so what they want to be able to do is, if you have an existing system in the field and maybe your compressor dies, okay, so the compressor's gone, we can buy a replacement compressor, put in that unit to keep that unit going. They don't want to have to, prematurely replace, good existing equipment in the field. So they've specified that you can make these components into the future for R410A as long as they're going into existing equipment. If we do make these products after the dates that I'll talk about on the next slide, so if we do continue to make these products, we have to put a label on them that says for servicing existing equipment only. Okay, so that you can't use these components in new equipment. So that's the delineation there. Now, they also add this little piece in the rule that's very important to all of you. Okay, so it says any person who assembles, contracts for, takes ownership of, or operates a system, so that's probably most of you, is responsible for adhering to this rule when we're talking, especially when we're talking about systems. Okay, because but they also do say, consumers, so homeowners don't have to understand the rule, but the contractors and the people selling the equipment need to make sure they understand this and follow the rules and follow the dates and all that kind of thing. Manufacturers are not really subject to the rule for systems because we only make a part of it. It's when it gets to the field where everything gets put together, where it's finally, technically to them considered to be manufactured is when you put that refrigerant in it. So it's really important for all of us to make sure we follow the rules and understand those rules.
Kevin, can I ask you a question about that?
Yeah, go ahead.
I get asked all the time, how long will we be able to purchase components for 410A? Do we know is there any reason why that wouldn't be indefinitely, or is there a time they might cut that off? Or?
Yeah, at this point, it's indefinite on those things. Now, condensing unit is kind of is subject to a little gray area at the moment. So industries asked that EPA to stop the production of condensing units themselves. We would still be able to make condensers and compressors. So we're waiting. EPA's kind of agreed that they're going to do that. So we're waiting on a rule that does explain that. So we do expect that condensing units are going to be banned some point in the near future, I would expect. But we do expect the other pieces, condensers, or the condenser coil itself, the compressors and the evaporators. We expect those to be to not have any end date anytime soon. So,
thank you.
Yeah, great question. All right, so let's talk about the dates. So for residential, commercial air conditioners, heat pumps, and chillers, okay, for that broad category there, EPA is requiring that for any equipment manufactured beginning 1/1/25, it'll have to have a GWP 700. Okay, we'll talk about some of the GWP levels here in a little bit for various refrigerants, but it has to be less than 700 for anything manufactured beginning 1/1/25. So we're just we're just 20 days away from that, right? So the end is here for new R410A equipment.
It's done.
They also do allow, however, that equipment, as long as it's manufactured before 1/1/25, you've got until 1/1/28 to actually get it installed. Okay, so this is for packaged equipment. Okay, so equipment that's it's the definition meeting product, meaning it was charged in the manufacturing facility. Okay, so you get 3 years to install it as long as it's made this year. Then split systems are a little different. So split systems must have the refrigerant charged by 1/1/26, as long as that equipment was built in before 1/1/25. Okay, so the condenser, the compressor, all that kind of stuff still has to be built this year, but you get a year to get those pieces together, installed, the piping all put in there, and the refrigerant charged in the field. So you get until basically 12/31/25 to get all that done. Okay, then VRF, they give it kind of its own category. So VRF, you have to the equipment has to be manufactured before 1/1/26 or imported into the United States. That when I say manufactured, that also means imported into the United States. So the equipment will have to have a GWP less than 700 beginning 1/1/26 for anything manufactured or imported in the U.S. They did just this last week put out a new rule that said as long as the equipment is manufactured before 1/1/26, they'll give them an extra year as well to get it installed and the refrigerant charged. So that it has to be installed and charged before 1/1/27. And then they created a new category for data centers. Okay, so data centers, the GWP doesn't have to be less than 700 until 1/1/27. Okay, so there is an important distinction I need to make too, though, is that when the AIM Act was written, it did not give what's known as preemption to the EPA. So the EPA can set kind of the maximum levels So any of these numbers that I'm showing here are the max levels that the EPA has set. States can actually go to lower values if they want to. Okay, so for instance, on data centers in the state of California, they didn't. Already wrote a rule that said they want the GWP less than 750 beginning 1/1/25. Okay, so data centers don't get the extra 2 years in California. Okay, so states can go to lower values. New York State has a proposal to have their GWP to be less than 10 for a lot of products as early as 2028. Now, it's not a final rule yet. We're still waiting on that.
Did you say
California
less than
is
10?
also working on some. Yeah, less than 10. And California is also working on some rules that would be either less than 10 or less than 150. So states can go lower, and it'll be interesting to see, you know, if states decide to do that or not. So big challenges still ahead of us.
Wow.
So this map of the U.S. here kind of represents what we've been doing building code wise. Okay, if you do get a copy of the presentation from Tony, up here in this upper right hand corner, there's a link there, and you can go to AHRI's website, and they've got an A2L building code map, and you can click on any state, and it'll tell you the applicable building codes and all that, the process, and you know all the status of all those things in any given state. So it's a pretty handy tool to look up your state and how things are going. But this summary here shows what we've been doing in the various states. So the states in that light green color are states where we had the ability to go in and update their building codes in some way. We either did, we had an interpretation letter from a building code official, or we were able to make amendments to the building codes or something like that in those states. The states in light blue are states where we didn't have that ability. And some of these are states that, you know, don't have a statewide building code. You know, they have various cities that have their own codes and things like that. So what we did in those states is we've actually passed legislation. So we worked with the state legislatures and got the governors to sign into law, very simple laws, which usually are just a few lines, and they usually say something to the effect is, as long as the EPA is approved a refrigerant for a given application, and as long as that appliance is following the appropriate safety standard, that the building codes cannot prohibit the use of that refrigerant. Okay, so it's usually just a few lines that say that. So it's very easy to read and understand. So that's what we did in those light blue states. The dark blue states, California, Oregon, and Washington, they did both. So they passed building codes and they passed legislation. The state of Alaska, it's kind of red here. The state of Alaska, the building code, you know, the state fire marshal has basically said he thinks that these refrigerants are all allowed in their state, and he doesn't see a problem with it. But he won't really write a letter that says that. So we don't have super clean documentation, but they say it's fine. The state of Nevada, they're still trying to finish everything up. The state of Nevada is divided into two halves, the northern half and the southern half. And both of those authorities say they'll have this all finished by the end of this year. So we got a couple of weeks left. But so we do think they're going to be done, which means this is going to be legal in all 50 states. Now, we had some states that were kind of cutting it down to the wire, but we did finally finish it. So we're good to go on all of our building codes. When we look at Canada, there may be some in the audience from Canada today. Canada is a little different. So in Canada, we have their safety standard is what's known as CSA B52. So it's pretty much aligned with ASHRAE 15, which is the refrigerant safety standard in the U.S. So they align it together. It's on a 5-year code cycle, and it was released in 2023. So in December 23, so about a year ago, they released the final version of it to align with ASHRAE 15, which would allow A2Ls in building codes in Canada. Now, we've got to update all those building codes to allow these A2L refrigerants. About half the provinces in Canada auto-update their building codes. Then the other half have to do work. So currently, Canada doesn't have any national plan to do, sector-based control like the EPA is doing, where they're giving dates to certain, for GWP and certain product types. They haven't done that yet. They've talked about maybe 27 or 2028, but nothing's finalized or announced yet. Now, it's important to note, as U.S. manufacturers will not be able to manufacture R410A systems, after a couple of weeks here, meaning we can't manufacture a 410A system and export it to Canada or anywhere else in the world. And unfortunately, manufacturers in like Mexico, they could manufacture a 410A system, ship it through the United States, and and into Canada, and the EPA can't stop that. But as a U.S. manufacturer, you're not able to do that. So, so there's some difficulties there, but we're kind of having to deal with that. So this is kind of an update of some of the various provinces and their timelines. Most of them are expected to kind of have their building codes updated by the end of this year. Some have already got it done. We do have a couple that are kind of probably squeak into the beginning part of next year. So, but in general, we will be able to use A2L equipment in Canada as well. All right, so let's talk about the refrigerant flammability a little bit, because I'm sure you're kind of thinking, why are we going to a flammable refrigerant? What does that mean for me? That kind of sounds a little scary. What do we do about that? So this little graphic on the left here represents how they test refrigerants for flammability. So this is representing it's a 12-inch flask, right? A round cylinder here, round sphere, where they test these refrigerants. So what they do is, in the top of that, they'll inject the right oxygen to refrigerant mixture, the right concentration, and then they've got this electrode that can impart enough energy in there to light these refrigerants. And then we've got this 90-degree angle. So what happens is, when they light one of these refrigerants, if it stays within that 90-degree angle, then it's considered a class 1 refrigerant. Okay, so one of those, quote, non-flammable refrigerants, even though it does light. So as long as it stays within that, it's a class 1. If it goes outside of that, it becomes something else. Okay, so here's a picture of lighting one of these class 1 refrigerants, so something like R410A. So if you light this, it will actually light, and you see that it just barely stays inside that 90-degree angle. Okay, so that makes it a class 1. Well, now let's light a class 2L, these refrigerants we're talking about going to now, So when we light one of those, it just barely goes outside that 90-degree angle. Okay, so you can just see it kind of trickling out. When you look at these two pictures, they look almost the same. So in reality, even though we've changed the classification and we're doing all these safety things, the flammability of these is very similar. Okay, and in reality too, the oil that's in these systems is flammable. The compressor oil that keeps the compressors working. That oil is flammable. So if you have a leak and you spray a mist of that oil tends to be more flammable than even the refrigerants. And it's the same oil in most cases from when we're going to the class 1 to the class 2Ls. Okay, so
and these
not a
are
real big difference here, even though it does sound scary. Now, if we look at a class 3 refrigerant, so something like propane, when you light it up, it goes boom. Okay, it fills up the whole thing. All right, so they are significant. Yeah, Tony?
Oh, I was
Did I
just
lose you? Okay.
I was just kind of
so these really go when you light up these. They're significantly different than a class 2L. So as we look at some of these requirements that we have for safety, right? We want to make sure we're super safe. These new safety safety standards have all these new requirements in them. So things like we now have leak detection, okay, and we'll have charge limits based on LFL. Okay, LFL is the lower flammability limit. Okay, so the lower flammability limit of any combustible gas, okay, it's the lowest concentration of that combustible gas to oxygen ratio. Okay, so if we keep the concentration of the gas low enough, we don't have enough gas to actually ignite that refrigerant. Okay, you need enough concentration to light it. Okay, so if we stay below LFL, we can't actually light one of these refrigerants. Okay, so that's the whole concept behind all this in the safety. Okay, so we got the lower flammability limit. When you look at some of these refrigerants, R454B, we'll talk more about the refrigerants in a moment, but it has a lower flammability limit about 0.019. If you look at 60335, if you look at ASHRAE 34, it's 0.022. These standards, unfortunately, they're typically a little bit out of sync. One will come out, and then a couple years later, another one will come out. So they don't always have the same values in them. If you look at R32, it's very similar. It's 0.019. So these are kind of the two refrigerants that are out there to replace these R410A. So they're very similar. If you look at propane, however, it's very low. 0.002. So it requires 10 times less refrigerant, to ignite one of these things. So it's much different as far as flammability is concerned. And then our safety standards require us to detect leaks. And if we detect 25% of the LFL, Okay, so again, very safe, 4 times less than LFL. If we detect 25% of the LFL, then our leak detector is required to go off and send out alarms. Okay, so then we also have some charge limits. So in ASHRAE 15, now there's several different sections in ASHRAE 15, and I encourage you to, especially if you're a building designer or something like that, you want to read all the different things and understand all these. So I'll give you an example of one of these. So in section 7.6.1.1, there's a calculation for EDCV, or effective dispersal charge volume. Okay, this is the max amount of charge you can have in a given volume, okay, a given space in your building, okay? And this is specifically with air circulation, either constant or activated by a leak detector, for human comfort, okay? So there's a few different categories when you look in there, and I'm not gonna go into all of those, but this is just kind of an example of one of those. So this EDCV is this V effective, okay, effective dispersal volume, so it's the volume of your space, times the LFL, okay, which you talked about on the previous screen, times the concentration factor, which just happens to be 0.5 in all these cases, times an occupancy factor, okay? And that occupancy factor is 0.5 for institutions. So this is places where it's hard for people to get out of the building, so like a hospital or a nursing home or a prison. So they want to have less charge in some of those buildings, since they know it's going to be harder to get people out. Or it's 1.0 for anything else, okay? So that's kind of one of the equations that goes into determining how much charge can my unit leak into a given space, or how much charge can my unit have for this given space, okay? And that's to keep it below that LFL value again. Okay, and we only look at the largest individual refrigeration system in that piece of equipment. So we're assuming that only one system would leak. We're not assuming, you know, if a unit had 2 or 3 refrigeration systems in it, we're going to assume that they don't all leak at the same time. Okay, that's kind of the concept behind this. And then our unit nameplate is required by UL 60335 to have a minimum area calculation on it. Okay, and this value may be a little bit different than the value that you calculate from ASHRAE 15. So we'll, on our unit nameplate as an air conditioner manufacturer, we'll have this calculation on there. So you'll see it, and then you'll need to do the building calculation, and then you kind of take the worst case scenario, okay? So that's how these standards work. All right, and then I'll just talk about one other thing in ASHRAE 15, and this is about pipe shafts, okay? So if you have a pipe shaft where we're running refrigerant tubing for, you know, split systems or VRFs, things like that, there's this in section 912.1-5, for all refrigerants, you know, this is something that's just been in there for a while. Basically says if you're doing refrigerant piping that's going between 2 or more floors or ceiling assemblies, you got to enclose that in a fire rated shaft, okay? But then if you go to A2L refrigerants or B2L refrigerants, that pipe shaft needs to be ventilated, either naturally or mechanically. Then when you go to A3s or, you know, class 3 refrigerants, there's even more things you have to do. So there's, again, just a few of the examples. You know, you really need to understand ASHRAE 15 if you're one of these building designers. Okay. All right. So let's talk briefly about the refrigerant detection systems. Okay. So we're now going to have sensors in our equipment that will detect leaks, and they'll be in various places, and it probably depends on the manufacturer where we do certain things, but what our safety standards kind of give us some guidelines and some requirements here. First off, it needs to have a 15-year lifespan. Okay, if you're familiar with, you know, refrigerant leak detectors that maybe are in a mechanical room, a lot of times those, you know, they're much larger, more expensive refrigerant detectors, but they also require calibrations and things like that. These you know, they do understand, you know, these are going to go into lots of different products. They may be building some residential products, but lots of commercial products and various things. And, you know, homeowners, building owners, they're not going to be checking on these all the time, right? So they want to make sure they have a long life. They want to make sure they're immune to what's known as poisoning. Poisoning would be if, you know, if we have a big leak and it saturates the sensor, that sensor needs to recover when that leak is fixed and the refrigerant's dispersed. Okay, so they want to make sure it doesn't, you know, it's a term known as poisoning, but it basically means that sensor's dead. So they had to make sure that was the case. They had to be self-calibrating. Okay, so again, we don't want to have to calibrate those every year because that just probably wouldn't happen, right? And they have to be UL certified. There's a new UL certification for that. And then they have to alarm at 25% of the LFL value. Okay, so these are all things that the UL safety standard has put in that these sensors have to meet. So there's various companies that are out there that are manufacturing these sensors. And then finally, they also have to auto reset as well. So whenever the event is over, they need to be able to reset. Okay, so if we detect a leak or we have a loss of the sensor, if the sensor dies for whatever reason, it has to do a few things. Okay, first off, we need to activate the supply fan. Okay, because these refrigerants, they're heavier than air, and if we have a leak into the building, we want to make sure that refrigerant's well mixed. If we had a low area in a room or something, a low spot, these refrigerants, even though we've done the calculations to make sure we can't put too much refrigerant in a room, if we have a low area, we could actually have those refrigerants kind of fall down and kind of pool in a certain spot, and you could get above LFL in one of those areas. So we want to activate the supply fan, and we want to ramp it up to max speed so that we can really mix the room up, so that we mix that refrigerant around and we don't ever get below LFL. Okay, so that's kind of the concept there. We'll lock out the compressor so that we don't continue to pump that refrigerant out, and then we'll activate an alarm relay. Okay, and that alarm relay is to do a few things. First off, it's to tell us, tell the building, right? This alarm needs to be connected to the building. Tell them, hey, we've got a leak and we need to do some service here to fix this leak. If it's a VAV system, we want to tell the VAV boxes to open up because we need to increase the supply fan speed. We're going to pump a lot more air. You better open the VAV boxes or we're going to have a problem. Okay, so we need to make sure and do that because we're going to increase that airflow. And then we're going to reset that alarm after it's cleared. Now, the other part of this is really important is that we really need to make sure when we're installing this equipment that we get the building commissioning done as well. Okay, we want to make sure and test these sensors to make sure that the building's going to do what it's supposed to do, right? If it's a VAV system, we want to make sure those VAV boxes open up. We want to test that alarm relay to make sure that the building is notified that there's a leak. Okay, so I'm sure that's going to vary by manufacturer, but in general, I think at least with my company, one of the things you'll do is you'll go unplug the sensor, and that'll simulate a loss of sensor. So, and like I said, I'm sure various companies will do different things, but you want to make sure you do that building commissioning to make sure that the building does what it's supposed to in case there's a leak. Because 10 years down the road, maybe we've got new service people, whatever, they may not be watching this. We want to make sure the building does what it needs to do automatically if there's ever a leak. All right, the other thing that we had to work on as an industry was transportation of our equipment from our manufacturing facilities to the job sites. Okay, because U.S. Department of Transportation never recognized an A2L refrigerant either. Okay, so if we didn't get something done to recognize A2L refrigerants, the DOT was going to force us to treat these as an A2 or an A3 refrigerant. And under those classifications, you would have to ship all these products under hazmat rules. So you would have hazmat trucks and hazmat permits and special routes and a lot of cost, and probably we don't even have enough hazmat drivers to transport all these types of equipment. And the risk is much lower than a Class 2 or a Class 3 refrigerant. So industry worked with the U.S. Department of Transportation to get a couple of special permits. Okay, so there's two different permits. Okay, the first permit is for any equipment for units with less than 44 pounds of total refrigerant in that unit. Okay, and these permits are granted to companies that manufacture the equipment. So for instance, we have a single permit number for any product that we make with less than 44 pounds of refrigerant in it. Okay. And this particular permit is a complete exemption of any of the hazmat rules. So we don't have to have any special labels, no hazmat trucks or drivers or any of that kind of stuff. So complete exemption. They do specify, however, that you can't have any air or water transport under this special permit. Okay. If, for instance, you're on an island or something like that and you got to ship by water, you will have to get a job-specific permit for that particular unit. Okay, so that's a different permit than what I'm talking about here. These permits are granted to a company like mine who manufacture equipment, and we just have two. We have a single permit number for this one, and then we have a single permit number for units between 44 and 5,000 pounds of refrigerant. Okay, so the second permit isn't exactly a complete exemption, but almost. Okay, this one does require that we put special labels on the outside of the unit. Okay, so we'll have this flammable gas label it's about 4 by 4 inches by 4 inches. It has to be on at least two sides of the unit when it's shipping. Okay, so you will see that on these larger units. They also add an additional stipulation that you cannot ship these in an enclosed vehicle. Okay, so you can't ship it in a closed truck for any of these larger units. And again, no water or air transport either. They also say the permit needs to go aboard each vehicle that ships this. So for instance, if it goes from a manufacturer to like a rigger's yard or a distributor or something like that, it sits there a while and then it goes to the job site after that, that permit needs to be in that second shipment as well. Okay, so it needs to stay with it until it gets to the final job site. Then they also stipulate that if there's ever an accident, right, there's ever a wreck, the truck ever wrecks and gas is released, that has to be reported to the U.S. Department of Transportation. So, if you're using third-party shippers or something like that, where maybe the manufacturer's not involved, or, hotshot drivers, things like that, make sure they know the permit's with it. So, they will want to know that. But again, no hazmat requirements, none of that special thing that's going to be required. All right, so let's compare refrigerants a bit. Okay, so we've mentioned we've got to be GWP less than 700 here in just a few weeks on anything manufactured. So if we look at R410A, it had a GWP of 2088. Okay, so it's almost 3 times higher than that limit that we're going to be forced to follow here in the next couple of weeks. So we've kind of got 2 refrigerants really out there to replace 410A. So one of those is R32. Okay. It has a GWP of 675, so it's just below that 700 limit. The nice thing about 32 is a pretty low cost refrigerant. It's a single component. Okay, many of the refrigerants we talk about are blends. Okay, even R410A, it's a blend. It's actually a blend it's a 50-50 blend of 50% R32 and 50% R125. So we've actually been using 32 for many years here in R410A. But since it's a single component, it winds up costing less. So it does cost less. Some of these blends can be a little bit expensive just because some of the components in the blends can be more expensive. Okay, so that's a nice thing for 32. Now 32, the unfortunate thing about 32 is it has a pretty high discharge temperature. The temperature leaving the compressor going to the condenser coil tends to be about 40, 50, maybe even 60 degrees hotter compared to R410A. Okay, so that has a few implications. Some of the components can cost a little more, probably not too big a deal, but the bigger deal here is really the development cost. To use this refrigerant, you really have to do extensive redevelopments of the products, redesigning all the coils and things like that to deal with this higher temp. So, and the concern here can be that we may not have a long time before the next reduction in GWP limits, depending on what various governments do. So, distributing those development costs over shorter periods of time can lead to more price increases, which a lot of us want to try to eliminate. So, kind of a negative to the side on R32. Then the other refrigerant we have out there is what's known as R454B. Okay, it has a GWP of 467. So 32 has about a 50% higher GWP compared to 454B. It is a more expensive refrigerant, okay, and that's because it's a blend. So it's about 69% R32 and about 31% 1234YF. And YF is, when you talk about refrigerant, it's a fairly expensive refrigerant. It's the refrigerant that's used in most automobiles today for the air conditioners and automobiles. So it is a blend, and it does make it a more expensive refrigerant. But the nice thing about it, it's a pretty close drop-in for R410A. Okay, so if you just take it and put it in a 410A system, they run very similar. The efficiency, the capacity is very similar. Now, when I say drop-in, I mean as a manufacturer, and we're developing products. Okay, I want to emphasize it's completely illegal to have an existing 410A unit in the field and put 454B in it. Okay, that's because that 410A unit was never designed under a safety standard that allowed A2L refrigerants. Okay, so it doesn't have the leak detectors. It doesn't have all the component testing that went involved to be allowed to use an A2L refrigerant. So that's all in a unit that has that 60335 standard. So completely illegal to take 454B and put it in your existing 410A unit in the field. But as a manufacturer, as we're developing products, we don't have to do as much with this one, so we can save on some of those development costs, and we don't have to pass those along to our customers. And some of the components can cost a little less, but in general, that development cost is kind of where it's at on that decision. So, some companies have decided to use 32, some have decided to use 454. So it's, just kind of company by company, what you decide to use. And then as we kind of look at some alternatives out there, okay, because of course everyone wants to see what's coming up next, what are we dealing with next? And I don't have that crystal ball yet, but there are a lot of things that people talk about, and I'll kind of talk through some of those. First off, if you're looking at R410A and the properties it has and the efficiency and capacity and all that, there's really nothing else out there available at the moment at much lower than the two that I just discussed. Okay, so there's really nothing else out there. Now, if we start to look at something like R22, similar to the properties R22 had, which we used before 2010, there is a refrigerant out there, around 150 GWP that could work. So it's a different blend, but it has some properties that allow it to work. There would be significant redesigns we would have to do with this, and maybe a few compromises. Equipment might get a little bigger. It kind of depends, but that one is, a possibility. If GWP levels are set at 150, we'd have some options there that aren't too terrible. Chemours, which is one of the refrigerant manufacturers, they've announced that they're searching for a new molecule to solve this problem. They said when they developed 1234YF, it cost about $1 billion. Okay, so big time money goes into developing these refrigerants. So, and big rewards for them if they can find that magic refrigerant. So we'll see what comes of that, I guess. If you want to go much lower than 150 GWP, though, at what we have at the moment, okay, you start to look at what are kind of known as low pressure refrigerants, something like R134A, which is something you see in chillers today. The problem when you start to get to these low pressure refrigerants is that just small pressure drops in like the piping, through a refrigerant valve or through the refrigerant piping, small pressure drops really start to dramatically affect the performance because we start at a lower pressure, right? So, a 1 to 2 pound PSI pressure drop can start to really hurt performance. Whereas with something like R410A, which is much higher pressure, if you have a couple of PSI drop there, it doesn't really affect anything. So the way you deal with that is you have to go to like larger pipe sizes. Okay, so larger refrigerant pipes, which increases cost. It increases the amount of refrigerant charge in the unit. You also have to have larger compressors because these lower pressure refrigerants require much higher mass flows. So you got to pump a lot more refrigerant, which requires a larger impeller on your compressor. So the compressors get bigger, compressors cost more. So there starts to be these trade-offs as we go to these lower values. There's a refrigerant out there known as 1234ZE. It's actually, I think, used in some chiller products today. It has a GWP of 7. Okay, 7. Anything below 10 is considered like ultra low, so it would fall into that category. So that's really good. The unfortunate thing about ZE is its capacity is not very good. It has about 25% less capacity than 134A does. So, to get the same capacity, you got to have a 25% bigger unit in most cases. Okay, so equipment gets bigger, it costs more. So again with the trade-offs, right? Another unfortunate thing when we talk about like heat pumps, especially when talking about maybe cold climate heat pumps, if you were to use this refrigerant in one of those type systems, this refrigerant at -2 degree refrigerant temperature is actually 0 psi. If you get below -2, it starts to go negative, meaning it starts to go in a vacuum. So if you have an outdoor coil and it's like maybe below 10 degrees outside and your suction temperature gets below -2, then if you had a leak in that outdoor coil, it would actually suck outdoor air into that coil instead of releasing the refrigerant out. So we would bring non-condensables and things we don't want in our refrigeration systems into that unit. So that would cause a lot of problems. So another detractor for that ZE, if we were trying to use it in a heat pump, which, as people want to electrify, we've got to go to more heat pumps. So, another kind of strike against ZE there. And then we also talk a lot about natural refrigerants. Okay, there's a lot of people who are proposing we need to be going to these quote natural refrigerants. Things like, believe it or not, ammonia. Ammonia is R717. Ammonia was really one of the first refrigerants that was used in the early 1900s. Now, great thing about it is that, it's one of the few refrigerants that has a GWP equal to 0. Okay. But the unfortunate thing about ammonia is it's toxic. Okay. So it falls in that B category for toxic refrigerants. You got to do things like, if you have a leak in the building, you got to evacuate the building, right? ASHRAE 15, our safety standard, it doesn't even allow ammonia in what's known as a high probability system. This is a system where, like, if we have a DX coil where air blows across it and blows into the space, if there was a leak in that DX coil and it could get into the space, that's what's considered a high probability system. So ASHRAE 15 doesn't allow ammonia in that. You can only do ammonia like something like a chiller, something like that, where a leak wouldn't go directly into the building. Okay. And then another unfortunate part about ammonia is it's corrosive to copper. So we could no longer use copper piping. We couldn't use copper in our coils. So we'd have to use something else in that case. Another refrigerant that a lot of people are talking about is R290, which is propane. Okay. Has a GWP of 3, so it's in that ultra low category, but it's an A3. Okay. It's very flammable to really explosive in the right concentrations. It'll put out a pressure wave. It can knock down walls. It can, propane can be pretty dangerous. There's over 7,000 barbecue grill accidents a year, and those are, kind of sitting outside. So in buildings, it's definitely a concern. With A2Ls, it took years to get A2Ls approved in building codes and get through the fire marshals and all those type folks. They're very concerned about using propane in air conditioning. So it'll take a lot of work to get there in the United States. You are seeing this in Europe, but Europe is very different than the US in how we adopt codes and safety standards and things like that. In the US, currently the max charge is 0.33 pounds, 150 grams. Folks are working on maybe getting to 1 or 2 pounds in the future, but when you look at air conditioning, typically air conditioning is going to be 1 to 2 pounds a ton of refrigerant. So wouldn't make a very large air conditioner. Maybe some room air conditioners will have it. For larger stuff, it's going to take a lot more research, development, a lot of code work, a lot of study before we could probably get propane to that point. And then, of course, the other big one a lot of people like to talk about is R744, which is CO2. Okay, CO2 has a GWP 1. It's kind of the definition of GWP, and it's an A1, so it's that non-flammable, non-toxic type refrigerant. Okay, so great benefits right there. The unfortunate thing about CO2 is a very high pressure. Okay, for reference, at 1,000 psi at 84 degrees. Okay, so it's very high pressure. When you look at 410A, for example, at 84 degrees, it's 250 psi. So considerably higher pressure. When you look at 120 degrees, something you might need for condensing on an air conditioner in warmer states, it gets to almost 2,000 psi. So extremely high pressures. So in a lot of cases, you're probably going to be dealing with stainless steel refrigerant tubing instead of copper like we use today in both our between components and in our coils. So much more expensive to use stainless steel compared to copper. You're probably going to be doing welding instead of brazing. So a more expensive technique. You got to have higher trained technicians, all these kinds of things. So a lot more goes into that. Now it is a very good refrigerant for heating. Okay, it's pretty efficient for heating. So there are water heater products out on the market that are heat pump water heaters that are using this refrigerant. The unfortunate thing in cooling, especially for air conditioning, the efficiency is not very good. It tends to be maybe 30% less than what we're used to. So again, equipment would have to maybe get bigger or do various things to get that efficiency back. So all these kinds of things kind of lead to CO2 at this point being a pretty expensive to apply in an air conditioner for certain. So a lot of research has to be done to maybe use some of these other things, and that there's a lot of research ongoing to do that. So as we kind of wrap this up here, we got to transition next month, right? We're 20 days away from the end of R410A being able to be manufactured in air conditioning in the U.S. So it's been a good run for 410A. We started in 2010. Some companies started quite a bit earlier than that, but it's time. I guess we're going to move on to something else, right? So it's really important to make sure and train your teams, train your customers, because a lot of new things happening. Like I said, when we opened up, Really, I think this is probably the biggest transition I've been associated with in the industry in my 28 years. Just because it's impacting all of us, right? Manufacturers, our designers, our customers, everybody's being affected by this. So make sure everyone understands it. But like I kind of been leading to throughout this, we need to respect these A2Ls. They are a little more flammable than we're used to, but it's not something to be afraid of. It's definitely not propane or natural gas or something like that, which we have been using in our buildings for 100 years to heat our buildings through furnaces. So. And we've got a lot of safeties in our equipment. Industries work very hard to make sure this is going to be very safe. So just want to close you out with that concept. So